Hello students, welcome to the fifth video of Chapter 1 Solid State. In this video, we shall study about packing efficiency of metal crystal in simple cubic lattice, body-centered cubic lattice, and face-centered cubic lattice. Along with this, we shall study about the number of particles and unit cells in X gram of metallic crystal. Let's get started with packing efficiency. Like coordination number, the magnitude of packing efficiency gives a measure of how tightly particles are packed together. Packing efficiency is the fraction or a percentage of the total space occupied by the spheres or particles. The formula of packing efficiency is equal to volume occupied by the atoms per unit cell divided by total volume of the unit cell multiplied by 100. Let us now calculate the packing efficiency of metal crystal in some simple cubic lattice. In simple unit cell, particles are present at the 8 corners of the unit cell. Total number of particles per unit cell is equal to 1 upon 8 multiplied by 8, that is equal to 1. As shown in the figure, the distance from one end of the cube to another end is A, that is the edge length. To calculate the packing efficiency for simple cubic lattice, first we will take the step radius of sphere. Let A be the length of each side of the unit cell as shown in the earlier figure and R be the radius of the atom. For simple unit cell, A is equal to twice R. Therefore, R will be is equal to A divided by 2. As you can see in the figure 1.9, R is equal to the half of the edge length. Step 2 is to calculate volume of sphere. Volume of a normal sphere is given by 4 by 3 pi r cube. So substituting the value of r as a by 2 in the formula, we get 4 by 3 pi into a divided by 2 whole cube. Solving it, you get 4 by 3 pi into a cube divided by 8. Simplifying this equation, you get volume of a sphere is equal to pi by 6 a cube. Now step 3 is to calculate the total volume of particles. Simple cubic unit cell contains only one particle. Total volume occupied by the particles in the unit cell is already calculated as pi by 6 a cube. Now packing efficiency of simple cubic unit lattice. The volume of a unit cell is given as capital V, which is the cube of edge length, that is a cube. Packing efficiency according to the formula is volume occupied by the atoms per unit cell divided by total volume of the unit cell multiplied by 100. Substituting the value as volume occupied, which is your calculated answer, pi by 6 a cube, volume of the unit cell as a cube multiplied by 100. Solving the equation, we get pi by 6 into 100. If we substitute the value of pi as 3.14, we get the answer for packing efficiency as 52.36%, which indicates that the volume unoccupied in the simple cubic lattice is 47.6%, which constitutes the voids or the holes. Now let us see the packing efficiency of metal crystal in body-centered cubic lattice. In first step is radius of sphere or the particle. In BCC unit cell, particles occupy the corners and in addition, one particle is at the center of the cube. As shown in the figure, A and F are the particles at the edge or at the corners and C is the particle at the center of the cube. So figure 1.10 shows that the particle at the center of the cube touches two corner particles along the diagonal of the cube. Now to obtain the radius of the particle, that is the sphere, Pythagoras theorem has to be applied. To calculate the radius of sphere or the particle in BCC crystal lattice, we have to consider triangle FED, which is at the bottom. The angle FED is equal to 90 degree. Therefore, FD square, that is the hypotenuse square, is equal to FE square plus ED square. Both FE and ED are edges, so that is equal to A square plus A square, that is equal to twice A square. Let this be equation 1.8. For triangle AFD, that is the triangle which is vertical, angle ADF is 90 degree. Therefore, AF square, that is the diagonal of the cube, is equal to AD square plus FD square. Now AD square is the edge, so it will be A square, and FD square we have calculated above. So substituting of equation 1.8 into equation 1.9, we get AF square is equal to A square plus twice A square, which is equal to 3A square. Taking square root on both the sides, we get AF is equal to root 3 into A. Now AF constitutes the three spheres, and it is made up of the radius of sphere at the corners and diagonal diameter of the sphere in the center. Thus, figure shows that AF is equal to 4 times R. Substituting this in the equation 1.10, we get root 3A is equal to 4R, and hence we get the radius of sphere R as root 3 by 4A. Next, step 2 is to calculate the volume of sphere. Volume of sphere particle is generally given as 4 by 3 pi r cube. Substituting the value of r, we get volume of one particle is equal to 4 by 3 pi into root 3 upon 4a whole cube. Solving for the bracket, we get 4 by 3 pi into root 3 cube divided by 64 into a cube. Solving the entire fraction, we get root 3 pi a cube divided by 16. The third step is to calculate the total volume of particles. Unit cell BCC contains 2 particles. Hence, the volume occupied by particles in BCC unit cell is equal to twice the volume of sphere. So that is twice root 3 pi a cube divided by 16. Solving the ratio, we get total volume of particles is equal to root 3 pi a cube divided by 8. Let this be equation 1.12. Now the last step is the step 4, packing efficiency. Packing efficiency as given by the formula volume occupied by particles in unit cell divided by total volume of unit cell multiplied by 100. Substitute the values from the step 2 and step 3. We get root 3 pi a cube divided by 8a cube into 100. Substituting the value of pi, we get the answer as 68%. Thus, 68% of the total volume in BCC unit lattice is occupied by atoms and 32% is empty space or void volume. Let us now calculate the packing efficiency of metal crystal in face center cubic lattice or CCP or HCP lattice. As seen in the figure, the sphere A and C are at the corners of the cube, whereas the middle sphere is in the face ABCD. Step 1 is to calculate the radius of particle or sphere. The corner particles are assumed to touch the particle at the center of the face ABCD. The triangle ABC is a right angle triangle with angle ABC is equal to 90 degree. And AC is the diagonal of the square that is the face of the cube. Now, according to Pythagoras theorem, AC square, which is hypotenuse square, is equal to AB square plus BC square. Since AB and BC are edges, it will be equal to A square plus A square. That is equal to twice A square. Now, because AB and BC are same, hence AC can be written as root 2A. Let this be equation 1.13. Now the figure 1.11 shows that AC is equal to 4 times R. that is the 4 radius. Substitution for AC from equation 1.13 we get root 2A is equal to 4R. Therefore R will be equal to root 2 upon 4 into A. Solving the ratio we get R is equal to A divided by 2 root 2. Step 2 is to calculate the volume of the sphere. Volume of one particle is given as 4 by 3 pi r cube. Then substitution for r from equation 1.14 will give us volume of one particle is equal to 4 by 3 pi multiplied by a upon 2 root 2 whole cube. Solving the ratio you get 4 by 3 pi a cube into 1 upon 2 root 2 whole cube. That is equal to volume of one particle is pi a cube divided by 12 root 2. The next step is to calculate the total volume of particles. The unit cell of FCC lattice contains 4 particles, hence volume occupied by particles in FCC unit cell is equal to 4 into pi a cube divided by 12 root 2, which is equal to pi a cube divided by root 3 root 2. Last step is to calculate the packing efficiency of the FCC structure. Volume occupied by particles in unit cell divided by total volume of unit cell multiplied by 100 is the packing efficiency. Substituting the values from the steps which we have calculated, volume occupied by particles in unit cell is pi a cube divided by 3 root 2 a cube, where the a cube in the denominator is the total volume of unit cell, whole multiplied by 100. Cancellation of a cube takes place to give us volume packing efficiency is equal to pi upon 3 root 2 into 100. Substituting the value of pi as 3.14, we get the packing efficiency is equal to 74%. Thus, in FCC or CCP or HCP crystal lattice, 74% of the total volume is occupied by particles and 26% is void volume or empty space. The table 1.3 shows the expression for various parameters of particles in terms of unit cell dimension for cubic systems. If it is a simple cubic unit cell, the relationship between A and R is equal to A by 2, which is equal to 0.5A. Volume of one particle is given as pi a cube divided by 6. Substituting the value of pi, we get it as 0.5237 a cube. And last, total volume occupied by particles in unit cell pi a cube divided by 6, you get it as 0.5237 a cube. Next is BCC unit cell. The relationship between A and R is equal to root 3 upon 4A. Substituting for root 3, we get the answer as 0.4330 A. Volume of one particle is equal to root 3 pi a cube divided by 16, which is equal to 0.34 a cube. And total volume occupied by particles in unit cell will be twice that of the volume of one particle. So 0.34 into 2 is equal to 0.68. Since the contribution of the particles in BCC is 2. Next is FCC or CCP. Radius r is equal to root 2a upon 4. Substituting for root 2 we get 0.3535a. Next, volume of one particle is pi a cube divided by 12 root 2, which is equal to 0.185 a cube. The total volume occupied by particles in unit cell is equal to pi a cube divided by 3 root 2, which is equal to 0.74 a cube. So following table will show the summary of coordination number of particles and packing efficiency in various cubic systems. For simple cubic lattice, the coordination number of atoms is 6, 4 in the same layer, 1 directly above and 1 directly below. Packing efficiency is 52.4%. For BCC structure, the coordination number is 8, 4 in the layer below and 4 in the layer above. Packing efficiency is 68%. For FCC or CCP or HCP structure, coordination number is 12, 6 in its own layer, 3 above and 3 below. And the packing efficiency is 74%, which is the highest amongst the three. In this slide, we shall be studying about number of particles and unit cells in X gram of metallic crystal. The number of particles and number of unit cells in given mass of a metal can be calculated from the unknown parameters of unit cell, namely number of particles, that is n per unit cell, and volume A cube of a unit cell. Density ρ and molar mass capital M of a metal are related to each other through unit cell parameters as shown below. Rho is equal to mass upon volume. All of us know this. Now substitute for mass upon volume as number of particles in unit cell divided by volume of unit cell multiplied by molar mass upon Avogadro's number. Therefore, finally, rho is equal to n upon A cube multiplied by capital M upon n suffix A. Then molar mass of the given particle, which will be equal to rho into A cube into n suffix A divided by number of moles, where n is the number of particles in unit cell and A cube is the volume of unit cell. The number of particles in x gram of metal. Since molar mass capital M contains n times particles, therefore x gram of metal will contain x into Na divided by capital M particles. Substitution of capital M will give us number of particles in x gram is equal to small x into Avogadro's number divided by rho into A cube into Avogadro's number whole again divided by small n, that is equal to x into small n divided by rho into A cube. This will be your final formula to calculate the number of particles for any solid state figure. Number of unit cells in x gram metal. Since n particles correspond to one unit cell, therefore x into n divided by rho into A cube particles will correspond to x into n divided by rho into A cube multiplied by 1 upon n unit cells. Therefore, number of unit cells in x gram of metal is equal to x divided by rho into A cube. Further, the number of unit cells in volume capital V of a metal is given as capital V divided by A cube, which is the edge length of the cube. Thank you students for watching this video. I hope you are well versed now with the type of unit cells and their packing efficiencies, explaining to us that FCC or CCP or HCP structure is the most packed structure amongst the three. In the next video, we shall study about the numericals based on these topics. Until then,